Hi, in this video, again involving subwoofers system design techniques, we will cover comparisons between doing straight lines of subwoofers in front of the stage, physical arc lines or virtual arc lines by the use of electronic delay, and we will compare them with using a technique called end-fired, that is directional to the front and that produces attenuation to the back, and also gradient. So in the first part we will compare only straight lines versus arc lines, and we will understand the directivity differences, and the most important, what is the price to pay in the sound pressure level with these different variations of using straight lines versus arc lines. Then we will explain the difference between the directional effects of end-fired versus gradient, and also the SPL differences between them. And the last part is that we will compare all of them, and in order that you can have a better understanding of this. It's very important to point that for doing designs in all these techniques and take decisions like in what is the distance between the subwoofers, or in the case that we use electronic delays or even polarity differences, I have been using the calculator by Merline by Bambin that is in this link. And if I go right now to a browser and go to that link, well, this is the page of the calculator. And what you have to understand is that in order to download this calculator, you need to scroll down, and it is here. So the latest version is the 1.10 is this, and you can download, is free to download. And my advice is that you download the manual, and please read the manual to understand how to use it. And this is an addendum on the manual for all the new features that has been added from version 1.0 to 1.10. What else can I tell you about this calculator? Well, there will be another video explaining all the calculator in detail. It's in this section of videos about subwoofers. Okay, and on top of this, it's important to point that all of these techniques are basically explained by the same person. His name is Harry Olson, and all of them except one are included in a book called Acoustical Engineering. And in other words, straight lines, arc lines, electronic arcs, and something that was explained in a previous video, that is the window tapering for doing smoothing in the lateral side lobes, and the end-fired, all of them are included in the book from 1947, Acoustical Engineering. The last one, that is gradient. Gradient is in a document for a conference, AES conference from 1972 in New York. It is when Harry Olson explained gradient. So, well, and just for the record, the straight lines, the title that Harry Olson give to this is called just straight lines source. And in the case of the arc lines, the title that he was doing is curved line source, and in parentheses he says arc of a circle. The electronic arcs is called beam tilting by phase shifting, and the window tapering, it's just tapered straight line source. End-fired, well, it's the same as people knows, and the gradient is the same as people knows. Okay, so in order to understand just from the beginning these differences, okay, in the calculator of Merline, in the upper left, we have the area where we will define if we want to do a physical array or delay array, end-fired and gradient. This is the one, and the distance between the speakers, the ones that we will use in the straight lines or arc lines, will be 2.5 meters. In a previous video, it's explained why 2.5 meters. And I will use 8. So now, when I use 8, you have here the parameters of the spacing between speakers in this area that I am showing, and it's very simple. You can see here the polar patterns of all the different frequencies in the bandwidth, and you can put microphones in a configuration that the microphones are, let me see, I think it's number 3. Yes, are deployed from the central of the array to the edge of the array. And if from the central of the array and to the edge of the array, you can see the frequency response from all the speakers. In a previous video, it was explained that basically when you are in the front of the array is where you are having enough attenuation that basically you can say that you are outside directivity. This black graphic, it is the last microphone, and the red graphic, it's the central microphone. And we can also learn that we can change frequency. So in this case, 30 Hertz, it's wider directivity. And then 40 Hertz, slightly narrow. 50 Hertz is more narrow. 63 Hertz is more narrow. 80 Hertz is more narrow. These are the things that was explained in a previous video. And also the display angle, the total display from one side to the other side, locating the minus 6 dB point, is what you can see here. So you can see that 31 Hertz is wider than, let's say, 80 Hertz. 80 Hertz is more narrow. This is what we can understand by the polar patterns. But again, as I say, this is another video that goes in this direction. Important thing with the straight lines, the distance is crucial because as soon as a frequency wavelength matches the distance as 360 degree, a frequency, then there will have lateral summation. This will occur where in this calculator is the red color. In this case is 136 Hertz. So if I show 136 Hertz turn on, you will see that we will have lateral summation here in the polar pattern, 136. This is the lateral summation. And if I introduce here 136, you can see here lateral summation. And if I deploy the microphones in a way that I can have 90 degree, okay, 136 here, if I remove a low pass filter here and I put, let's say, 200 Hertz, you will see this is the lateral summation in this frequency. However, this is not a problem here because we have the low pass filter earlier than the lateral summation. And we can say that in this yellow cell, 91 Hertz is the latest safe frequency before start to go into lateral summation. So if I write here 91 Hertz, then you still don't see lateral summation. However, this is explained in more detail in a different video. The other important thing is that we can transform with this calculator straight lines to arc shape. So if I introduce in this cell 45 degree, then we will have a 45 degree section of a circle. So this is the arc of 45 degree. And you can see here that all the speakers are being located or deployed in the edge of a circle. In this case, the circle is having a 22 meters radius. So this means the focal point is 22 meters behind these 8 speakers. And these are the positions for the speakers. And these are the frequency response from the front to the side. In this case, if I do the option number 2, then the microphones are deployed from the central one to the outer one in a way that the last microphone is in line with the focal point. Important to point out is that in this case, exactly the microphone that is in the focal point that matches with the 45 degree total angle is already outside the coverage area. And as it has been explained in a previous video, if you want to understand what is the usable directivity, the usable directivity is 67% of the total arc shape. So in this case, if the total arc shape is 45 degree, the usable directivity is this multiplied by 0.67, that in this case says here 30 degrees is the maximum angle before the variations between the different microphone positions is not crossing the barrier of 6 decibels. So here we don't have more than 6 decibel variation at any given position. And important thing to understand is that if we have arc shape, we have wider in the directivity in the front and more narrow in the back. But if we transform this to electronic delay straight line, that is what I am doing. This is a straight line, and the electronic delay values from the centers, the 4 and 5, to the outers, the number 1 and 8, it is here. So this is basically applying electronic delay to simulate the additional time propagation from being in the arc position. And the difference between the electronic delay and the physical arc is that with the electronic delay, the rear part is wider as the front part. And with the physical arc, the rear part is more narrow and focus more energy in the back. That is the main difference, and this has been explained in another video. Okay, the other technique that is explained here, well, that is used with this calculator for doing design is M-fided. In this case, for doing M-fided, I will use 4 speakers. And 4 speakers, why? Well, this is a matter of another video, a video that is focused only on M-fided. In this case, the distance that I will use is 1 meter. And you can see here that we have 4 speakers, we have 1 meter. In this case, the arc-shaped angle is disabled, so it's not used anymore. Now it's only the number of speakers and this distance. And what we can see here, if I select 180 degree microphone distribution from the front to the back, we can see now the summations in the front versus the attenuations in the back. And in this case, we don't see the microphone number 8 because it's been turned off. Let me turn on all the microphones so you can see that in the back what we have is basically comb filter, while in the front we have summation and then smooth attenuation side by side. So attenuation for this microphone and this microphone, etc., etc. One important, and these are the polar patterns that we have for the end-fided. Let me write here 90 degree. That is the limit that we are using for all these examples, from 31 to 90 degree. And you can see that in the M-fided, the higher frequencies has more narrow pattern, and in the lower frequencies we have wider pattern. The directivity variations at the minus 6 dB point compared to the center, it's that the lower frequencies is around 348 degree opening, and the higher frequencies 122. So if I go right here 31 degree is wide directivity, but if I go right here 90 degree is more narrow directivity. So this is important thing to understand with the M-fided. M-fided, on the other hand, also you can see here that it has more electronic delay, more to the frontal position. And sorry, it's the position, the electronic delay, more electronic delay to the frontal position. That are the characteristics of M-fided, and that this is wider in the directivity at lower frequencies, narrow in the directivity at higher frequencies, something that we can call proportional directivity. And for reasons that are explained in another video, it is for having a usable bandwidth of attenuation in the back, we need to use 4. Then the last of the techniques that you can apply in this calculator is the number 4, that is gradient. In this case, gradient only works with 2. So this is 2 speakers. And in this case, you can see that the number 4 is being disabled and the grid for the arc is disabled. In this case, I will explain with this separation, 1.35 meters, the 2 speakers. And in a video that is focused in gradient will be explained why 1.35 meters. Important thing here is that you can see in the calculator that how the speakers are being deployed. The second speaker here is behind the first speaker, and the second speaker has electronic delay and polarity reversal. Important thing with the gradient is that the polar pattern variations is not as wide as in the M5 is very, very similar directivity. However, the lower frequency is more narrow and the higher frequency is wider. And you can see that in the usable bandwidth, 31 to 90 hertz, the 31 hertz is 192, 90 hertz is 248. So these are the difference. In other words, the gradient is wider directivity in the higher frequency, narrow directivity in the lower frequency. And well, this is the calculator that in a different video is explained everything connect with the calculator, include how to read the bandwidth graphic and how the phase graphics and individual level graphics and how to use the window function for the tapering. Okay, so now let's start for the primary explanation. For this primary explanation, since there will be several arrays that we will use, straight lines, arc lines, straight lines with electronic delay, M-finite and gradient, it's very important that what we will observe here will be not only colors, but we will measure what is the behavior of every one of these configurations at different positions. So, as you can see here, we have isometric, plant, front, and section. And we have 4 microphones at 5 meter distance, 4 microphones at 45 meter distance, and 4 microphones at 85 meter distance. So we have 40 meters apart every set of microphones. And we will call microphone A to the ones that are in the center. Then this is the microphone 2, microphone 3, and microphone 4. So then we have from the center to the outer, center to outer at different distance to understand. And also we have a microphone in the stage in order to learn about the frequency response and the level for every configuration. So let's start with this. And the first configuration will be straight lines. And something that we know with the straight lines is basically if we are in front of the last speaker is where the directivity, where you are basically at the edge of the directivity. So if I go to the straight line and check here, then we will see that we are in line with the last speaker. We are like in the edge of the directivity. By the way, right now in this moment, I can see that this is reading SPL. Let me change this from reading SPL to attenuation. Okay, so now the color changes, and now this reads that the red is 0. But this 0 in reality represents 102 decibels for the frequency 63 that we are checking here. So we understand, okay, so this red represents 102 decibels, and every color is being defined by 3 decibels of attenuation, and we have visual range of 42 decibels in this graphic. Okay, so it's easy to see. Let me remove all of these drawings and use some arrows. Where is grid? Okay, so you will see that now this line to this line. If we cross these lines, then we will see that the colors becomes like more attenuated. So this is where we are like going outside directivity, outside the directivity. And if we change these straight lines versus arc, in the case of the arc will not be defined by these lines, but will be defined by the lines of the arc. So these lines connect the focal point to the latest speakers, these outer lines, and the inner lines, it's 67% of the outer lines, because in the outer lines we have variations from different positions that are more than 6 decibels, but in the inner arc the variation will be not more than 6 decibels. So this means that the inner arc is the usable arc for the directivity. So if I test in this frequency the arc, you can see that the directivity is wider compared to the directivity that we have with the straight line. The other important thing is to see that this is a lot of a lot of SPL, a lot of level in the back with narrow pattern. So this is narrow pattern, and in the front is wide pattern. If we are in the delay situation, in this case, in the delay situation, you can see that now we have sound outside the lines that in the straight line shows where the color attenuated. The important thing is that in the straight situation with electronics delay from the center to the outer, we can see that we have wide coverage in the back, similar to the coverage in the front. If I want to see in this configuration about the line with electronic delays, if I see the properties, you can see that the center speaker is connected to a channel called 1 left and right center. The next speaker says 2 left right center, then 3 left right center, then 4 left right center. This is the speakers to the left, and the speakers to the right is the same: 1 left right center, 2 left right center, two left right, 3 left right, and 4 outer. If I go to the processor, this is the first 4 channels, and these are the electronics delays: 1.1, 3.21, 6.55, according to the calculator by Merline, the subwoofer array designer, and these are the levels that we define. And then, by the way, these are the end-fired situation. In the end-fired situation, we have electronic delays, less delays in the back and more delays in the front. And in the gradient, we can see that we have the electronic delay in the back and polarity reversal. So these are the parameters used for these explanations. Okay, if I go to the straight lines, we can see that all the subwoofers are in the same channel. Channel 1, channel 1, channel 1, all the subwoofers are in channel 1. And if I go to the arc line, all the subwoofers are also in the channel 1. So this means that straight lines or arc lines only need one processing channel because they have to do exactly the same. Is when we use electronic arc or end-fired or gradient, when we will need multiple channels of processing. Okay, so now let's see what happens with end-fired. In this case, the end-fired is not pointing to the front. Why is not pointing to the front? Because then in the center will be a lot of power compared to the outers, and then the outers will be poor in power. So what we are doing here is trying to make that the sound of one system goes to cover basically half of the audience, and the sound of the other system, that will be this, will be point to the other half of the audience, in a way that when we play all together, we don't have so much summation in the front. You can see that the colors here in the front or going outside here are similar. So this means that it's similar, and here it's similar. We are trying to have a pattern that will be more uniform, but with a price to pay. The power alley, this dark blue is power alley, and this power alley is easy to explain. Exactly in the center, the distances are identical. So this is 0-degree phase difference, no power alley, but summation. But the summation is not so intense because we are aiming the system outwards. But however, in this position, in this power alley, then what we have is that this system is closer and this system is far away for half cycle. So this means that we have 180 degree in this position. And this is the price to pay, but the stage is more clean than being in the front at reciprocal distance. What happens with the gradient? Okay, in the gradient, we are doing now similar thing. So this is the gradient left. It's focusing in cover the left of the audience. The right gradient will cover the right of the audience, and the two systems together will have the interaction where the level in the center, it will be similar to the level in the outer parts at similar distance. So you can see that at this distance is the same color as this and the same color as this. So we are having a uniformity, except that we again have the power alley because in this we are closer to this array and we are far from this array, but this power alley will be less depth or less profound as if we are using the subwoofers as omnidirectional. So why? Because in this case we are having directivity into the system. I forgot to mention that here this stage is cleaner. Compare a reciprocal distance front and back, this stage is more clean. Important thing to point out is that if I select, let's say, only one speaker, you will see that this, only one, okay, this speaker will be omni, okay, and if we select only one speaker here and only one speaker here, then you can see that the pattern of the cancels goes more to the side. So this is very powerful power alley compared to when we have the full arrays. When we have the full arrays, you can see that we're used to have here attenuation, we don't have anymore. Why? Because the system is, one of the system is pointing the energy in one direction and the other in another direction. So this counterattack the power alley to the sides, and we have only the more profound power alley close to the center. Okay, however, what we are watching here, it's important to point out that in this representation we are watching relative attenuation. This says that the level that we can obtain is 110 decibels. So what I will do is reassign to make that the red is 110 decibels. So we have here the system that is called the gradient. The gradient in the near field, when we are closer to the arrays, let me clear this and let me show only this system. Okay, and let me take this part and this part. Okay, if I do a super zoom in, we have two subwoofers here in the back. This is one channel, two subwoofers here in the front. This is another channel. So imagine this. If I am, let's say, at this position, it's very terrible drawing, let's say this. My distance to the first component is this, and my distance to the second component is this. The proportion of distances means that in the near field, the second one, it's been attenuated to the first one. So the total summation is like, let's say, the decibels of this one plus the decibels of this one with longer distance. That means inverse score low, that will have less level, but this will be the total summation. What happens if we have the M-fided? In the M-fided, the situation is, well, a little bit more dramatic, because if I am in the near field, I will have distance 1, distance 2, distance 3, and distance 4. So if we compare the proportion of distances for every one of these, the second subwoofer here in the near field is like travel like 2 times distance. So the contribution of the second subwoofer will be 6 decibels less than this one. And the next subwoofer travel more distance, maybe it is around 7 or 8. And the last one travel like 3 times the distance. So this will be like around -9. The summation of all these subwoofers in the near field will be slightly less powerful than when we have the gradient. But what happens when we have subwoofers in line? Oh, if we are in the near field, let's say that I am here in the center, okay, in the near field, this distance and this distance is identical, so they will have summation, but this is longer, so this excess of distance will make that this have a little bit less level, let's say -3, terrible 3, and then this has more difference in distance compared to the first distance, so this maybe is around -8, and this will have more excess of distance, so this means that this will have around -9 or -12 or -11. On top of this travel more distance, this means phase shift, phase shift, phase shift. So in the near field, all these 8 subwoofers that we have, they will have not really summation. This will happen for the straight line, but it will be more dramatic if we are in the arc shape, because now the distance increases in this example, and in the delay one, the distance also increases. So let's do here control, sorry, let's come here to the, what is the name? Isometric. So now we have then the configuration that we will play here, the straight, the arc, and the delay, and the infinite, and the gradient. So turn on these areas that will show the colors. Start with the straight lines and see from all points of view. Okay. No, sorry, start with gradient, because gradient is the one that in the near field, oh, but I have a chaos because I have many systems. Okay, now, gradient is the one that in the near field will show more level, that here closer to the system is 110 decibels. But we can see that here in this area, oh, let me delete all of this. Here in the back, or well, just before the back, we have this color, that this color is around the 89. Is this color. What happens if we change? And also let's mark that here is the same color. So just as reference that we have this color. And if we go to the infinite and to this, we will see that with the infinite, the colors are the same as with the gradients, except that in the infinite, we don't have in the near field 110 decibels, but we have 107 decibels that you can read here. So this means that this red is not the red number one, but it's the second one. Then, if we go to the straight line, you will see that with the straight line, we will have the same level that we had here with the infinite and gradient. However, here we have a lot of attenuation, and in the near field, we don't reach 110 decibels as in the gradient, but we have 102 decibels. Of course, in the straight lines, we have a lot of separation between the speakers, so in the proximity, you cannot have summation. So comparing to the gradient, we have like 8 decibels less power in the near field with the line, but in the distance, in the coverage area that is the center, is similar to gradient and M5. What happens when we do arc shape? With the arc shape, we will see that, oh my god, the level that we used to have here, we drop 6 decibels more. So this means that we are around 77 decibels. So instead of having 83 decibels in this distance, we have 77, but you can see that in this width we have similar level, and in the proximity again we drop level, so instead of 110 we have 101, so we have 9 decibels less in the near field than when we was with the gradient and the end fired. And what about with subwoofers with electronic delay? Subwoofers with electronic delay, it's similar to the subwoofers with arc shape in the frontal area. In the back, the electronic delay is wider, remember? But the color that we can see, again, this is 77 decibel SPL at this distance, and in the near field, it's showing 103 decibels, that is around 7 decibels less than when we was closer to the gradient or infinite. Okay, but something that may be even more interesting, because in this software Map 3D we can use microphones. In other words, the microphones will be deployed as a graphic of analyzer. So we have here a lot of distances, and let's start comparing what happens in the near field. Okay, in the near field we have these microphones. So I will remember that the first microphone is the one in the center, and then I will go outside. And at 45 meters will be the same, at 85 meters will be the same. We're going from the center to the outside. And we will do this investigation from 5 meters, 45 meters, and then 85 meters, and the last part will be the stage. Okay, so what happens if I select the straight line? Remember that in the straight line, let me use grid lines, okay. we will have good coverage, good frequency response inside these two black lines, but we'll have bad frequency response outside this. So this will a lot of level attenuation that basically with this line will be comb filter. So inside this will not be comb filter, outside this will be comb filter. I have to point out that the second microphones at all the positions is exactly in the line of the last speaker. So this is the second microphone at 5 meters, this is the second microphone at 45 meters, and this is the second microphone at 85 meters. Okay, so now this is the microphone in the center. Central microphone with the line, this is the straight line, second microphone, and I will group straight line, 5 meters, and it's the center. Okay, or microphone number 1. Okay, this will be used as a reference, and I will show here in red color. What happens if I go to the second microphone? You can see that the second microphone is like in the limit of directivity, and if I do offset in the blue graphics, that is the second microphone, you can see that the variation is between 3 and 4 decibels. If we see as SPL is this area that shows here SPL Z, that shows that the center microphone shows 102, and the microphone that is in the limit with the last subwoofer says 98, so this means that we have around 4 decibel variation, DVZ. C means zero filtering, as in A weighting filter or C weighting filter. And if you are not familiar with the weighting filters that are used for SPL measurements, well, this will be a matter of another video. Okay, go ahead with this. Now, if I go to the microphone number 3, you can see, whoa, dramatic. The microphone number 3, it's really outside the coverage. And if we bring this up, the average of this is around 17 decibels. So if we compare in SPL, the difference between 85 to 102, it's around 18 decibels, okay? Now, if we see the last microphone, the number 4, it's even more attenuation. You compare microphone 3, microphone 4. So this is the differences between being close or far. If I chose by colors, you can see that outside these lines, you can see that the microphones number 2, it's just in the limit. Microphone number 3 is more attenuation, and microphone 4 is even more attenuation. Okay, we start to understand how the line is in the near field. But what happens if instead of the line, now we do, say no, now let's do the arc shape. If we go to the arc shape, in other words, this one, and we measure in the center microphone, the frequency response is slightly different to the straight line, but in the average SPL, you can see that the difference it is 101.7 versus 102.1 is 0.4 decibel difference. So this is hard to detect the difference, and you have a little difference in the response. Let me store this, and I will use the name arc 5 meters, comma, center microphone. And now this will be the one that we will use for comparison as what happens if you go out. Be aware that as soon as we are in this configuration, then the limit of the directivity variation start to be this line, and after this line the variation will be more, and this means that in this area here we are outside the coverage of the array that we can see when we do this prediction. So you can see we are outside the coverage of the array. So surely microphone 1 and 2 will be good. Man 1 and 2 will be very even. But microphone 3 is outside the coverage, and microphone 4 is out coverage in the near field. In the mid and far field, the situation will be different. So now microphone number 2, the variation is very small. How much? I think that barely 1.5 or 2 decibels. according to the decibelimeter, it is like comparing this one versus this one, 100.2 versus 101.7. It is what is 1.5 decibel relative difference between these two graphics. What happens if we go to the microphone 3? Now we are outside coverage, and microphone 4 even more outside coverage. Of course. So now let's go to the subs with electronic delay. I have to say that in the subs with electronic delay, it will be similar situation. The subs with electronic delay, microphone 3 and 4 are outside coverage. So let's come here, and the subs with electronic delay, in the near field the frequency response is slightly different, but it's similar characteristics, and the difference in level between doing the arc shape, that is this brown, versus the straight line with electronic delay, blue line, the difference in level will be not more than 1 decibels. You can see 1.1.7 versus 1.2.6 is 0.9 decibels. No, it's not even 1 decibel. Let's store this and let's call electronic line 5 meters in the center. Okay, and recall this with this color. And now if we go to the second microphone, the variations are less than 6 decibels, similar because we are in coverage. Then we are outside coverage in the microphone 3, and microphone 4 we are even more outside coverage in the near field. So what happens when we go to the end-fired? In this case, with the end-fired we have something interesting, because with the end-fired we are in coverage, and the coverage of the end-fired, we can see that if we see on axis versus the -6 is like this Y. So all this will be in coverage. And the opposite system is firing sound in the opposite direction, that is not polluting so much here, except a little bit of pollution in the central area. That is where we start to see the power alley. You can see here the power alley, it's here in the closer area. So let's see what is the response in the microphone number 1, 5 meters, and in the microphone number 1 with the end-fired, we can see a lot of attenuation here in 87 Hertz. Let's investigate having here a frequency that be close to 90 Hertz. Yes, this one. Okay, in this microphone position, it's clear to see. So the distance between the speakers make that in this area, we don't have good coverage. So here, this is a price to pay. Then in this end-fired, the near area is not properly covered here. Okay, that is what we see here, but it's not properly covered at 90 Hertz, while in the lower frequencies we have around 3 decibels more than when the previous one, that is the electronic arc. So, and what happens if we compare with the electronic arc in the SPL? The electronic arc is this one, 102.6, and this is 100.8. So in SPL we have 2 decibels less in the end-fired compared to the electronic arc. Okay, let's do this. This is end-fired 5 meters in the center microphone, and this is the one that we will use, will be pink color. What happens with the second microphone? In the second microphone, life is good again. And in the third microphone, well, a little bit of drop in power compared to the second microphone and third microphone and fourth microphone. So these microphones are good except the center. Okay. Now let's test the gradient. Gradient in the center. Test. And you can see that the gradient in the center is not having the cancel at the 90 Hertz that we had with the end-fired. Why? Because the gradient is wider directivity in the higher frequencies. sorry, the gradient, and the M-fided is narrow directivity in the higher frequencies. Let me test only one array, M-fided. And you can see the M-fided here at 5 meters. Oh, it's outside directivity. Ah, you understand. Now, if I test the gradient here in the near field, the gradient is Y directivity. Okay, so gradients and M-fided are not the same. Okay, so in the gradient we don't have this problem that we used to have in the M-fided. And if we compare with the electronic arc in the center, or with the physical arc in the center, or with the straight line, the gradient at 5 meters outperform all of them. Okay, very, very interesting to learn this. So let's store this and save this with gradient, gradient 5 meters, comma, center microphone, in order to compare what happens in other microphone positions. So, and this will be with pink color. Okay, so this is the same gradient now in the position 2, position 3, and position 4. Okay, seems to be good enough. Position 4, that is this one, is this one what happens if we play together. But let's see the position 4. Okay, we are here, that we have by the colors less level that in these colors that are more bright. Okay, so this means that the people here is like in the limit of directivity in the microphone 4 in the gradient. Okay, but what happens if now we test this in the second group of microphones, the ones that are at 45 meters? Because it will be different situation now at 45 meters. What I will do is delete all these graphics because I don't want to make mistakes. Okay, so now at this distance, this is the level that we have with the M5, so with the straight line. Straight line, 45 meters, microphone in the center. Perfect. And recall here. Okay, let's go to the next group of microphones. Microphone number 2 is already more than 6 decibel attenuation at around 80 hertz. So this means that if we go here to look at around 80 hertz, here you have 0 decibel, -3, -6. So yes, we are around close to -9 decibel of attenuation in that frequency. Okay, what about microphone 3? Outside directivity, and microphone 4, way outside directivity. So we have to remember that the lines are very good coverage just inside the line, and outside the line is not good coverage. Okay, now let's go to the arc-shaped subwoofers. In the arc-shaped subwoofers, now compared to the straight line, the arc line drop in level dramatically. Oh my god, and drop in level at around, compared to the line in the central position, this is dropping the line around, wow, 11 decibels. So let's see by the colors the straight line here in the center. Okay, and then the arc shape, the color is having a lot of attenuation. Okay, so the arc line improved the coverage, but the price to pay is that the SPL, the level, drops. So drops dramatically. And imagine that we have the mixing console here going from a straight line to going from an arc shape. The coverage is better with the arc shape, but the price to pay is less decibel SPL. And if we want to see as a number, wow, it's 88 versus 94. So this is around 6 decibel less SPL with the arc shape line. Let's store this with the name arc 45 meters central position. And this will be the one that we'll use to compare what happens when we go to the other positions. The second microphone position, some variation less than 6 decibels. You can see that it's less than 6 decibels. It's only 5 in this frequency. And in this frequency, it's around 2. And in terms of SPL, is 88.4 versus 88.6. So very even in SPL. Microphone 3, again, similar. We are 91 versus 95. So this is 4 decibel variation. And in SPL, the total variation in SPL is 87 versus 80, 88. Oh, it's 1 decibel difference. What happens if I go to the outer microphone? The outer microphone is where you start to see that you are approaching 90.9, 95.8 is 5 decibel variation, and the total SPL difference is 84.7 versus 88.6. So it's 4 decibel variation. So this means that in all the area we have less than 4 decibel variation with the arc, but with the price to pay less level than using the straight line. The same thing will be for the arc shape with electronic delay. So now this is with electronic delays, and if we go to the central microphone, you can see that the frequency response, whoa, is identical. Well, maybe not even 1 decibel around here. So it's similar to the arc shape. So the electronic arc is really doing the same as the arc shape. So this is electronic delay, comma, and this will be 45 meter in the central position. Now this will be with this color. And if we go to the next position, again, the variation will be less than 6 decibels. And in the headroom, we can read 88 versus 88.1 decibel difference with SPL meter. Then this is the microphone 3 and microphone 4. And in any one of these, we will have more than 6 decibel variation. So this means that the electronic arc is doing a good job. However, this electronic arc, at least in the center position, that we can think the center position is where the mixer guy will be, it is less powerful than doing a straight line. A straight line is more powerful in the center where the mixer guy will be. And however, the straight line will not have coverage outside the last, sorry, I have to come here. The straight line will have no coverage outside the last element. So now, let's take M-Fired at 45 meters. The M-Fired, it is 45 meters in the center. This is having no... I have many systems turned on. Okay, now. Okay, the M-Fired at 45 meters, that is this microphone position, compared to all of this, M-Fired has more level in the center, like around the mixing position, more level than the arc shape and electronic arc, and it's only barely 1 decibel difference. Let me test. 1 decibel difference in the higher frequency. See, yes, 1 decibel difference in the higher frequency. So this means that the straight line is, and in terms of SPL, it is 93.5 versus the, I have not saved this yet, versus this one. 93.5 versus 94.3 is around 0.8 decibel difference. The straight line in that position, it's better than the M-Fired at 45 meters. What happens in position number 2? Let me store this. M-Fired, 45 meters, microphone in the center, and recall here. So this will be our reference for comparing what's going on when we go out. This is microphone number 2, microphone number 3, microphone number 4. Okay, what is this? Well, this is the cancel of Power Alley, and it says that the cancel is exactly in 57 Hertz. So if I go and locate a closer frequency to 57 Hertz, let me go 55 Hertz. Now this will be closer to the more dark area, that is the stronger cancel in the M-Fired. what happens in terms of SPL variation from being in the center, versus being in the second position. The center is 93.5 and the outer is 87.6. So this means that the difference is 87 versus 93. So this is around 6 decibel variation in the terms of SPL with microphone 2. Oh, this is not so nice. However, this will be more powerful in terms of level in this microphone position that we use electronic delay and arc shape, because the electronic delay and arc shape, they have less level. What is the level that they have as attenuation? Around 6 decibels from the center of the end fired. So the end fired in the microphone 2 is not so good. It dropped like in SPL 6 decibels. But what happens now in the microphone 3? In the microphone 3 improves here, and here goes down as cancel number 2 and cancel number 1. It's around 30 hertz. So if I come here and select something around 30 hertz, okay, in this microphone, that is microphone 3, is where we have darkness. Okay, so now is this. However, in terms of SPL, this center microphone 93 versus this microphone number 3, 89, it's 4 decibel variation. This is 4 decibel variation. And if we go to the microphone number 4, now the microphone number 4, in terms of SPL, is showing 89.7 versus 93.5. It's around 4 decibel variation. So the disadvantage that we can see clearly here with the gradient, with the M-fired, sorry, this is the M-fired. I think that I have said gradient 2 times, but the reality is that this is M-fired. The disadvantage of the M-fired is this power alley, but the advantage compared to lines is that it covers more than straight lines, and compared to arc shape or electronic delay is that the final SPL is louder with the M-fired. What about gradient? Okay, let's see the gradient. Gradient will have the power alleys that the M-fired shows. So now go to the center microphone, is this one, and you can see that in the gradient, compared to the M-fired that it shows here, it's a little bit better in this portion of frequencies and a little bit poor in this group of frequencies. But in terms of SPL, this is 93.5 versus 93.4. So this is only 0.1 decibel difference in the gradient compared to the end-fired. Let's store this with the name gradient 45 meters in the center. Okay, and we have right now here again with pink color, so let's bring it. Okay, what happens in the microphone 2? Same thing, a cancel by power alley. Microphone 3, the power alley changed from positions, and microphone 4, a narrow cancel in the microphone 4. In terms of SPL, okay, headroom, that will compare the live trace versus the bottom one. Okay, this is the central position, that is the same. In the second position, you can see that we drop from 86.8 to 93.4. So this is around 5 decibel variation. In the microphone 3, this is around 4 decibel variation. And in the microphone 4, this is around 89, 93, 4 decibel variation. So your variation as SPL using gradient, it is between 5 and 4, depends in what part of the power alley you are. But in terms of SPL, it's louder than the gradient, and it's louder than the straight line, arc shape, and delay subwoofers. Okay, and of course the straight line is similar in the coverage area, but the straight line has no coverage outside the last speaker. Okay, let's now evaluate the same thing but at 85 meters. And for this reason, I will delete again all the previous traces. Okay, so now we have the straight line and the microphone is 85 meters. So you can see here the microphone, and we have here, let's compensate the time here, and let's do 85 meter straight line in the center. Okay, and let's recall here. What happens in the second position? You can see that this one, it's around 88 to 94. This is crossing the barrier of 6 decibels. Position 3, outside coverage. Position 4, outside coverage. Okay, we can see then that only in the position 1 and 2 is where we can say that the response is good enough. Actually, position 2 compared to the central position is not even 6 decibels. It's like a little bit less than 3 decibels in the difference. Okay, so what happens when we do arc line? The arc line open more. You can see now all the microphone will be with very small difference because everybody are in the same color. So this is the arc line. But what is the disadvantage? The arc line is way less powerful than the straight line. Oh, that's the price to pay. How many decibels of difference we have with the arc line to the straight line? Okay, we can see from 84 to 89, we have like 5 decibel less power in the arc line compared to the straight line. Remember that in all of these examples, we are using 8 speakers. So let's store this, that is our reference, and this will be 85 meters arc line center microphone, and this will be the one to compare. Okay, let's see the microphone number 2 is pretty similar, microphone number 3 pretty similar, microphone number 4 pretty similar, and we don't have 6 decibel difference at any given frequency. So if we compare in SPL, we can see now that we have 84 versus 84. Oh, same, but this is the same center microphone. Microphone number 2, 83 versus 0.8 versus 84. Not, it's 0.2 decibels. Then 83.4 versus 84, 0.6 decibels. And microphone number 4, 82.5 versus 84 is 1.5 decibel difference. So the variations in terms of SPL are minimized, but the total SPL is being dropped dramatically compared to the straight line. Okay, what happens if we do the electronic delay arc? It's the same. The response, the pattern is similar. So if we go to the measurement view, you can see, oh, it's the same in the center with the electronic as with the physical arc. So I will not even save this because the SPL, it is 83.7 versus 84 is 0.3 decibel difference. It don't work to save. So microphone 2, again, little variation, microphone 3 and microphone 4. And the difference between the center microphone to the outer microphone is what we can see, 1.2 decibels, and the previous microphone, 83.4, 84.6 decibels, and this to this it is 0.5 decibels. So this means doing the arc line, electronic delay line, is very, very uniform inside the coverage area that is around the good coverage area. In this case, it's around this line to this line. So this is the good coverage area. This portion is outside the coverage. How we can fix this? Doing a longer line. Longer line, it's another video that will explain that. Okay, so now let's go back to the microphone in the center and change to end-fired. Okay, end-fired in the center is more powerful than the arcs. So you can see, whoa, end-fired is way more powerful than what we have as the arc shape or the electronic delay lines. And if we go to the decibelimeter, you can see 88.5 versus 84. Oh, it's 4.5 decibel more powerful, the gradient compared to the end-fired compared to the to the arc shape with physically or with delay. What happens then, I will store this, and this is end-fired 85 meters, comma, center. Okay, and second microphone, and let's recall here. Second microphone, it's having dramatic attenuation here. Third microphone, now the attenuation goes in other frequency. Fourth microphone, the attenuation goes other frequency. What happens in terms of SPL? Okay, we have to compare this versus the tier 1. So this is 85. This is end-fired center, and this is end-fired center. This value should be the same. Yes, 88.5, 88.5. Okay, second microphone, we have 84 to 88. So this is in the boundary of the 4 to 8 is 4 decibel variation in SPL. Then the next microphone, 83 to 88, is 5 decibel variation. And this is 84 versus 88. This is 4 decibel variation. So even with this variation, the end-fired is louder than the arc line in terms of SPL. So gradient, well, gradient will be similar to the end-fired. Let's compare. Okay, remember that gradient has small variation in the lower frequency and in the higher frequency. This is part of explanation for other video that these differences. Okay, so store gradient 85 meters in the center, and recall this will be the pink one. Okay, this is the second microphone, the attenuation goes here. The third microphone, the attenuation goes in different frequency, and the last microphone goes in different frequency. If we compare SPL, you can see 80 and then microphone in the center. The first and the last one is the same microphone. The second microphone, 83.9 versus 88. This is this is around 4.1 decibel variation. This one is 2 to 8. This is 4 decibel. This is 6 decibel variation exactly. And this is 84.6. This is 4.4 decibel variation. So what we can start to realize is that if we do arc lines or electronic delay, everything is more uniform with the price to pay of less power. If we do end-fired or gradient, then end-fired or gradient will have more variation but more power overall. Even when in the cancel areas the total power is louder than when we have arc or electronic delay arcs. Something that we need to investigate right now is what happens in this stage. So this is the stage. How much sound is in this stage with the straight line? Let me delete the previous traces. And now in this stage, this is the stage with line. Stage with the line. Okay. What is the level with the arc shape? Well, with the arc shape, the level will go up a little bit. Why? Because the arc is focusing the energy into the back. So in the back, we have more level than with the straight line because this is pushing to the back. Okay, so we can see here more level with the arc shape. With the delay, it's not the same. It's kind of different, but we cannot say that it's overall more level because remember that the electronic delay, the back is wider, so the level drops. What happens with the end-fired? In the end-fired, the level drops way dramatically compared to any one of the lines. How many decibels in comparison to the straight line is 94 to 101 as SPL? Whoa, it's around 7 decibels, 7 decibels improvement when we are having the end-fired. And what happens with gradient? With gradient, Whoa, the attenuation is even better. In terms of SPL variation, it's 11 decibel benefit. So now what we can understand is that all of these different techniques has different consequences. And we can establish that if we use directional systems that are M-Fired or gradient and point out, you will have the more clean stage from all the situation. Of course that you can do arc subwoofers that can be cardioid. If you use cardioid subwoofers, well, the stage also will be as clean as with the gradient or the M-Fired. However, we know that the arc subwoofers or electronic delay subwoofers in the audience area will show less level everywhere, but with uniformity compared to the M-Fired or gradient. M-Fired or gradient will have more level in the audience area, but variation in the tonality by the power allays that we see here. And well, it is your decision what you want to do as a system designer. Do you want to have more SPL or do you want to have more uniformity in the response? The best advice that I can tell you is that if you have opportunity to test different configurations, you will figure out which one will be more in touch with your personal taste for the job. Thank you very much for your attention, and I hope that in the other videos you can be interested in watching also the other ones. Thank you very much.